Hello, hello. Welcome back again. Let's look at the last three questions for the Samuelson multiplier accelerator model. Okay, so the first question asks us, we're going back to the transition equation. Okay, we now know that this is called the transition equation. And it says, what are the conditions on the matrix A such that the system will be stable? So this is a memory test. We need to remember that for any matrix equation, the system is stable. The system is stable. Stable if all eigenvalues of A are bounded between -1 and 1 in modulus. Okay, modulus is absolute value for imaginary numbers. Okay. It's like the length, right? Like imaginary numbers are like vectors, right? So the modulus is this length here. Yeah, if this is the real number, this is R, and this is C, and then you have some point, okay? And then the modulus, the absolute value, will be the distance, the Pythagorean theorem. Okay, that's just a little aside. If you think about it, it makes sense, right? Because the absolute value is like measuring the distance from 0. If you go -1, you want to know how far are you from 0. So you flip it, you're 1. So same notion, just now that we have to think about the slopey angle because we can be off of the x-axis. Okay, so all the eigenvalues are between -1 and 1. Now, what additional condition is there if we want to generate business cycle-like oscillations? If we want oscillations, then all eigenvalues should have an imaginary component. An imaginary component, in addition to being stable. Okay? Because if they're not stable, then you don't have business cycles, you just have explosions. Why is this? There's a tight connection between eigenvalues and circles. If you're curious, go on YouTube, look this up. There's 3 blue, 1 brown is the resource I recommend. People that do math videos love to talk about this because it's very visual. You can look at circles and it's, oh wow, there's pi comes out of E and I, and wow. But yes, there's a very tight connection between imaginary numbers and circles, and oscillations are circles because they go up and down. It goes up, it goes down, and it goes around the circle. Okay, so this is the answer. We need the eigenvalues to be -1, 1 in modulus. And if we want there to be business cycles, we need that all of the eigenvalues should have an imaginary component. Okay, G is art class. I love art class. G says, consider a simulation of a model where a single shock of size 1 enters the model at time equals 0. Draw the resulting dynamics for the following scenarios. Smooth convergence, explosive growth, damped oscillations, explosive oscillations. Okay, so case 1. Smooth convergence. So we have our time. This is time. This is going to be yt. And at time 0, it says the shock comes in at time 0. So at time 0, we jump up. Maybe before in the minus times, we were going here. And then at time 0, we jump up. Let me switch colors. In the minus times, we were at 0. We were carrying along happily. And then this is, I oversold the color change. In the minus times, we were going along happily at 0. We get to time 0. We jump up. We jump up to here. And now we're going to have smooth convergence. So we're going to get the shark fin. It's going to come down nice, and it's going to get back to 0. Okay. I did make an assumption here. I assume that the steady state value is 0, but I won't blame you if you do that. Case 2, explosive growth. Well, explosive growth is compound interest. compound interest. You know how compound interest looks. It's the most powerful force in the universe. That's what Albert Einstein said, reportedly. We are carrying on at time equals 0. We jump up to 1. And then we don't come back to smooth convergence. We keep compounding. Instead of the shark fin, we just diverge to plus infinity. Okay, so we just fly off. Case 3. Case 3 was dampened oscillations. Okay, dampened oscillations are the guitar string. We're going to, once again, be in our happy negative time before time 0, before history begins. Everything's fine. And then it jumps up. And then we're going to not smoothly reconverge, but instead we're going to wobble about the steady state. Okay? And it's going to go closer and closer and closer and closer and closer, and eventually it'll get to the steady state. But it's going to look something like this. And then finally we have case 4, which is explosive oscillations, which, as I'm sure that you've already clicked off this video, but if you're still here, hello. I'm impressed. I'm impressed with your commitment to completeness. We're at our negative times, we go, we jump up to 1, and then we're still going to oscillate around the steady state, but instead of getting smaller and smaller, the oscillations will become larger and larger. And here we're going to oscillate between positive infinity and negative infinity. Okay, so that's everything that I have here. In the last one, we will do the bonus, and then we'll be done with this, and we'll move on to the Borrow-Gordon model. So I will see you there.